In this video I'm going to talk about ionic compounds and lattice energy because the book's explanation of these topics was such a train wreck. But first we need to talk about the types of chemical bonds. There are three kinds: covalent, polar, and ionic. Each one is different. In a covalent bond, for example Cl2, the electrons are shared equally. In a polar covalent bond, the electrons are shared unequally, for example HCl. And in an ionic bond, we say that the electrons are transferred. This happens because the compounds, when they bond, they try to reduce their energy, just like an apple falls off of Newton's head in order to reduce its gravitational potential energy. We categorize these compounds by their electronegativity. Electronegativity is an arbitrary measure of how much an atom pulls on another atom's electrons in a bond. The Pauling scale is one of them. Somebody a long time ago decided that fluorine should have a value of about 4.0, and all of the other values were determined based on comparing them with fluorine. In our class, we define a covalent bond as anything from a difference of 0 to 0.4 on the Pauling scale between the two atoms. In our case, chlorine's electronegativity is 3.16, and it's bonded to itself, so the difference is 0. A polar covalent compound is between 0.4 and 1.7. For example, in this case, hydrogen's electronegativity is 2.20, and chlorine's electronegativity was 3.16. So the difference is about 1, which is between 0.4 and 1.7. In an ionic bond is a difference that is greater than 1.7. In our case, chlorine is 3.16 and sodium is 0.93, which is a difference that is definitely greater than 1.7. In this video, we're going to be looking at the lattice energy of ionic compounds. So back to ionic compounds and lattice energy. Let's say I have two atoms, and let's say this one is chlorine and this one is sodium. And let's say I put chlorine reaches out and grabs one of sodium's electrons. Now the sodium has a +1 charge and the chlorine has a -1 charge. So even though the chlorine would like to run away with the extra electron, it can't, because the two are now bound by the charge. This happens many times when you have lots of atoms. So we end up creating this crystalline structure. Let's say the big ones represent chlorine and the small ones represent sodium. And this crystalline structure is held together by many of these positive and negative charges, which is where we get our salt crystals. This structure is called a crystal lattice, and the lattice energy is the energy that is released when the crystal lattice is formed. So if we remember, all compounds are created so that they lower the energy, and the energy doesn't just disappear, it is released into the environment. So based on our convention of defining the energy from the point of view of the system and not the environment, the energy released from the system is leaving the system. So our lattice energy is always negative. With that in mind, let's try to write an equation for the reaction between sodium and chlorine. So we take our sodium and our chlorine. Chlorine comes as Cl2 because it's a diatomic, and we only need 1/2 of it because we only need one chlorine atom. And that goes and gives us 1 NaCl. At room temperature, sodium comes as a solid and chlorine comes as a gas, and in the end we want a solid NaCl, solid salt. In order for sodium and chlorine to react, we have to first make them both into gases and take one electron away from sodium and give it to chlorine. So let's look at the sodium first. We start out with solid sodium, and first we have to make it into a gas, and then we have to take one of its electrons away. So according to these given equations here, for these problems usually equations will be given and you will be able to know the heats of each equation. Going from solid sodium to gaseous sodium is 109 kilojoules based on this one, and going from gas to an ion is 496 kilojoules based on this one. So we see that we had the sodium and then one electron was taken away from it, making it positive. And the total heat for this process is 605 kilojoules. And we just add these two up. And so we found the heat of formation of a gaseous sodium ion from solid sodium. We're going to do the same for chlorine. Chlorine starts out as a gas, so we don't need to vaporize it. But we do need to break the bond between one chlorine and the other. And then we have to take away one of chlorine's electrons, and we're good to go. So from here to here, this is 1/2 of 243 kilojoules. So that comes from this equation here. It says 243 kilojoules, but that's for forming 2 chlorine atoms. We only need 1 for this reaction, so we have to cut this number in half. That's what we did here. And going from chlorine to a chlorine ion, the energy is negative 349 kilojoules. That came from here. So chlorine, and we gave it 1 electron, and it became Cl minus. And then we just add these up again, and the sum for this process is negative 227.5 kilojoules. So then we're going to take our ions here, and we're going to say our sodium ion, which is a gas, plus our chlorine ion, which is also a gas, is going to create sodium chloride, or table salt, which is a solid. So since we have the heat of formation for both Na plus and Cl minus, we can use this equation. Now you'll notice that we have 2 gases, and we're trying to create a solid that has a crystal structure. So this is the energy of this equation is the lattice energy for sodium chloride. So we'll take our heat of formation equation, heat of reaction. Our heat of reaction is equal to the heat of formation of our products minus the heat of formation of our reactants. So looking at the last equation here, it looks like we took sodium and chlorine both in their regular states, and we made sodium chloride. And the heat of that reaction was negative 411 kilojoules. And that's the heat of formation of NaCl. So we're going to take that value for our products, negative 411, and then we're going to subtract it from the heat of formation, total heat of formation of our reactants, which was 605 plus negative 227. Uh, 227.5. And the result for this equation is negative 788.5 kilojoules. So the lattice energy, so this value is the heat of formation, is the heat of this equation, which is also equal to the lattice energy, because this is the equation that creates the crystal lattice from the ions that are gaseous. Let's take a look at a different problem. Another reaction that we can look at is the formation of lithium fluoride. So let's write an equation for this reaction. Lithium comes to us at room temperature as a solid, and we add some fluorine gas, and it's F2 because fluorine is a diatomic, which means that it can bond with itself. We use this to create lithium fluoride, and we want it to be a solid. And again, this is another ionic compound with a lattice structure. So we can solve it the same way we solved the previous problem. So let's get started. First, we take lithium, and it's a solid right now, and it needs to be an ionized gas. So we need lithium to be a gas. So we evaporate the lithium, and then we need to take away its electron. So we need to give it a positive charge. Fluorine comes to us as a gas. It's at room temperature, it's a gas. It comes in bottles, and it's really bad for you. And just like chlorine, if you let it out and start breathing it, it's not very good. So we are going to break the bond between the two fluorines so that we are left with just one. And then we take the gaseous fluorine and we need to give it an electron, so it needs to become F minus, which is also not a very good grade. Hopefully by doing this extra credit project, that won't be my grade after the final in this class. So first, lithium has to go from a solid to a gas, and to do that we have to give it some energy, 161 kilojoules. So this is 161. And then lithium gas, we take away one of its electrons. So here we had the lithium gas, and then we end up with a lithium missing an electron and an extra electron. So that is 520 kilojoules. And we add this up, and the heat of formation of gaseous lithium ion is 681 kilojoules. We can do the same thing with fluorine. So to break the bond here, we should always be careful when we use these equations, because sometimes they take one F2 and they make 2F. This time they were nice enough to take half F of an F2 and make 1F. So we can take this 77 kilojoule number and use it directly. So here it's 77, and we take our fluorine gas and we want to make it an F minus. So that means we have to give it an electron, and that's negative 328 kilojoules. And we add these up, we get negative 251 kilojoules for the heat of formation of a gaseous chlorine ion. And now we take these, just like we did in the previous problem, and we write another reaction. Here's our lithium, and here's our fluorine ion. And we want to put these together to create solid lithium fluoride, because we take the gaseous ions and we make a lattice, and this is the definition of the lattice energy So again, we're going to use the heat of formation, the heat of reaction. And the heat of this reaction is equal to the lattice energy, and the heat of the reaction is equal to the heat of formation of the products minus the same value for the reactants. And in the last equation here, this gives us the heat of formation of lithium fluoride as a solid, as a crystalline structure. So let's use those values, and we get negative 617 minus, and the sum of the heat of formation of the products, which was 681 plus negative 251. And this is equal to negative 1047 kilojoules. And that's the lattice energy of lithium fluoride. Now, if we remember from our earlier statement where we said that from the system to the environment, heat is always released when a lattice is forming. So from the perspective of the system, as our convention says, our heat of the lattice is going to be negative always. And here we have a negative sign, so we know that our answer at least makes some sort of sense. Now let's look at a different problem. This is the last problem. Here's another problem for solving the lattice energy. This time it's of silver chloride. Again, on the left we have these given values for the heats of some reactions. And if you press pause now, you can solve and then hit play again to check your answer. Alright, the correct answer is negative 915 kilojoules for the lattice energy of silver chloride. So let's take a look at how we got there. First, we have to take the silver, which is solid at room temperature, make it a gas by evaporating it, and take away one of its electrons. On the chlorine side, we have half of a chlorine diatomic. We break up that bond. Sorry, this is a gas. And we give it an electron. So let's take a look. From here to here, when we're evaporating the silver, that's 284 kilojoules. And from here to here, when we're taking away its electron, so we end up with an electron, that's 731. And the sum of those is 1015 kilojoules. Same thing with the chlorine, breaking up the diatomic bond. It's 244 if you want two chlorines at the end, but since we only want one, we're going to do 244 over 2. And from chlorine gas to a chlorine ion is this equation, which is negative 349. And the sum of those is negative 277 kilojoules. So now that we have the heats of formation for the silver ion and the chlorine ion, we can take these and we can write our equation for lattice energy. So we're going to take these gaseous ions and we're going to create something with a lattice structure. In our case, this is silver chloride. And it's a solid because we want it to have a lattice structure. So then we use our heat of reaction. The heat of this reaction, which is also equal to the lattice energy, is equal to the heat of formation of the products minus the reactants. In this case, the product is AgCl, silver chloride as a solid. So its heat of formation is negative 127. And we subtract our reactants. And the sum of that is, for silver, it's 1015. And for chlorine, it's 277, negative 277. and our answer is negative 915 kilojoules. So I hope you've learned a lot by watching this video, and if you feel like you haven't learned enough, you can go over this again in the Zoom Doll 7th edition AP Chemistry book. It's beginning on page 344 and ending on about page 346. And this is part of the Bonding General Concepts chapter, which is chapter 8. Thanks for watching.